So the last speaker today is Jesus Alberto Marquez from UNAM, who will speak on Newton polyhedra and holomorphic foliations.
Okay, thank you. Thank you for accepting my talk, and congrats, Frank. And well, in fact, I cheated a bit in my abstract. I changed the. It's pretty similar to what I promised, but I will share with you another stuff. So let me. It's about Newton polygons and holomorphic plane foliations, but it's about equisingularity and Newton diagram stability. For mu for Miller number, mu constant. Formations of Newton polygons, Newton diagrams for mu constant deformations of generalized curves, non-dicritical curves. So thanks David and Rogerio, because they already introduced what we understand. Well, they recalled what we all understand by generalized curves, and I will focus on the non-dicritical case. So these are objects where family of foliations introduced by Camacho, Neto, and Sad in their paper of 84, right? And I want to share with you a kind of analogous statement of both equisingularity and, well, in the context of Ler-Ramanujan theorem in singularity theory, and what Oka called Newton diagram stability for mu constant deformations of plane curve singularities. Okay, so let me recall what Oka proved in 1983. Okay, so in a very nice and short paper, Oka considered deformations of plane curve singularities. Say these guys are germs of analytic functions, or defines that defines functions on C2 times C around the origin, such that for any fixed t, this 0 goes to 0, and moreover, these germs, all them have an isolated singularity at the origin. So this means, that the Miller number of each of these guys is finite. Okay. And, well, the Miller number is the same recalled by David and Rogerio in their talks. Right? This is for any fixed t, the dimension over C of this quotient. So the Jacobian ideal, and we measure this, the codimension of this ideal, and this is fine. Well, being finite means that the singularity at the origin is isolated, and this, as they already recalled, is also, this measures the intersection multiplicity of the partial derivatives of each germs at 0, okay? So the algebraic, geometric interpretation of this. So what Oka proved is that given mu the formation of plane curves such that is mu constant, that means that the minimal number of each of these guys is equals to the initial one. And under the convenience assumption on the Newton diagram of the initial guy, if the Newton polygon on the initial coordinates is convenient, this is exactly what Rogerio told us before. So then the claim is that there exists an analytic family of coordinates, say phi t xy such that all of them are centered at the origin, and the Newton diagrams of if these guys in these coordinates coincide exactly with the initial one, right? So this is Oka's statement, and as it appears in his original paper. And well, a key ingredient in his proof is this the two-dimensional case of Ramanujan's theorem that says that for a mu constant family of plane curve singularities, this is the statement for the case n equals 2. So mu constant implies that the family is equisingular. Okay? So implies equisingular. Right? So Oka's proof is done by looking at how complicated is the initial Newton polygon, and he proceeds by induction of the blowing ups needed to make this guy simple. And in his proof, he used this statement that having mu constant condition implies equisingularity in the family, right? So all of the plane curves appearing in the family share the singularization process given by point blowing ups on the plane, or sequence of point blowing ups. And I don't know, any questions with this statement? No? This is equisingularity and Newton diagram stability for the case of curves, plane curves, sorry. And what I want to share with you today is the analogous result for, as you may guess, for the case of, like I said before, holomorphic plane foliations, holomorphic foliations. And as David and Rogerio told us, there are some classes of foliations that are nice, in the sense that they can be studied by means of focusing on the separatrices of them, and as Camacho, Lins, Neto, and Sad did in this paper, they talk about these guys that now we call, well, they define as generalized curves. And for me, during this talk, I will focus just on the non-critical ones. And, well, they prove a lot of interesting results on these guys. And I will try to sum up the main properties of generalized curves I am interested in. And given a germ of a generalized curve where omega is one holomorphic, the germ of one holomorphic form at C2, around the origin. In the non-critical case, the set of separatrices of defoliation is given by just a finite number of branches. So we can always write this guy as a reduced equation, being F germ. Okay. So I mean this step of S of F is the union of the reducible analytic curves passing through the origin. And what they proved a lot, Camacho, Lins, Neto, Sad. First, as maybe you know, the minimal number of defoliation F, or the one form omega, is equal to the minimal number of F, right? So just recall that given omega as A dx, B dy, this Rogerio and David already said this. So this is the intersection multiplicity of A and B these curves at the origin. So this is the same thing. And they prove this result, that in the case of generalized curves, having this, in the non-critical case, the minimal number of the one form omega is equal to the minimal number of the F, the reduced equation of its separatrices, And they also prove that, in fact, the foliation given by the kernel of omega is desingularized in the same way as its separatrices, right? So F and this Hamiltonian foliation are X-singular. Okay. Singular. Or it's the same as saying that the foliation is, the reduction of singularities of the foliation is the same as the resolution of singularities of this curve, okay? So, I don't know, what else? Well, in fact, here we can stop and then start thinking about how we could prove this kind of results, the equisingularity in mu constant families of foliations, or the Newton diagram stability for one forms. And one way is, what I did first was trying to mimic Oka's approach. So what I claim is that can be done. It's a nice exercise, I guess. But another way is invoking a result to Dulac in some cases that he considered in his thesis, and which was put in originality by Rouget, also in his thesis. So what Rouget did was to somehow to rediscover Dulac's comparison between Newton polygons for foliations or for one forms of vector fields and Newton polygons of functions, right? So Dulac, what I call Dulac-Rouget comparison, that is, as Rouget presents, is that in the case of, if we are given a generalized curve, non-dicritical one, and we consider a reduced equation of the union of its separatrices, then what happens is that the Newton diagram or polygon, it's the same, of the one form as defined by Rogerio is the same guy as the Newton polygon of F, that one can show that, in fact, this guy is the same as the Newton polygon of the Hamiltonian, or the differential of the functions, by definition. Okay? And, well, the way Rouget proved this claim, this comparison between the polygons, was by means of Camacho-Lins Neto Sad techniques. Okay, because one interesting thing, so how one can prove this statement is, so this follows from this following geometrical stuff. If we consider, I don't know, maybe it's not a good idea. Well, sorry. I don't know. Here is omega equal to 0, and here is better this way. What he proves is that given any curve that is not invariant by neither this foliation or the differential of f, I don't know. This is the same curve. What one can prove is that if we consider a parameterization of this guy, then using Camacho-Lins Neto Sad, the results, the order at 0 of the pullback is the same. So we have this equality that is a key tool in proving this equality. So just to get an idea, one can use this kind of techniques and then compare both Newton polygons. So if they were different, so one can find a vertex here that is not here, or vice versa. And then one can prove that this is an inequality. So that follows Dulac-Rouget's comparison. And I don't know, I have time. So using this Dulac-Rouget's and having in mind these Laird-Ramanujans and from one side, on one hand, sorry, these results of germs of functions. On the other hand, these nice results due to Camacho, Neto, and Sad. We can use this Dulac-Ruyes comparison as a bridge to prove results. So it's what I wanted to share with you. And what one can claim, what we can prove, sorry, is the following. So the foliation of the case of one forms this Le-Ramanujan and also Oka's theorem. So given a mu constant, the formation of, as you can guess, generalized curves, non-critical ones, so let's say. Then, what happens is, well, in fact, for the first, we don't need Dulac-Ruyes, but if we are given mu constant the formation of generalized curves, using Camacho, Neto, and Sad, this first claim, and Le-Ramanujans, we get as a corollary that the family is equisingular. Is equisingular. In fact, Mattei already considered a pretty close case where the initial guy was the differential of a function, so a deformation of a Hamiltonian foliation. And then, if we add the condition of that the first, the initial Newton polygon is convenient, just as Rogerio told us, convenient, using once again Camacho, Neto, and Sad, and now Dulac-Ruyes comparison, what we get as a kind of direct implication is that the Newton diagram stability, right? So the same conclusion that there exists an analytic family of coordinates as before. So it's thanks to Oka's theorem, such that these guys remains the same in the new coordinates, right? Okay, so I don't know. That's all I wanted to say in this short talk in 20 minutes. No, that's all.